Mrs. Intan Dewi Larasati MSc as the moderator, a lecturer from the Department of Food and Agricultural Product Technology from Universitas Gadjah Mada. And let me read the moderator's CV for you. Operator, please. Ms. Intan Dewi Larasati MSc have bachelor's degree from Universitas Gadjah Mada, and also the master's degree is from Universitas Gadjah Mada. Her research interests contain extraction methods, analytical chemistry and method validation, bioactive compounds, and functional food and beverage development. She also has several publications such as rapid microwave assisted anthocyanin extraction from rosal, colleagues method development and validation in 2024, optimization of ultrasound assisted cold brew method for developing rosal-based tisane with high antioxidant activity in 2023, and ultrasound assisted extraction of L-tryptophan from chamomile flower method development and application in 2023. Without further ado, Ms. Intan Dewi Larasati MSc, the time is yours.
Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, and a very good afternoon, everyone. Also, buenos dias, Prof. Miguel. Welcome to the session 4 as a part of 7 summer course, Faculty of Agricultural Technology, Universitas Gadjah Mada 2025. My name is Intan Dewi Larasati. You can call me Intan. And I'm a lecturer from Department of Food and Agricultural Product Technology, Universitas Gadjah Mada. And it is my honor to serve you as your moderator in this special session. Right now, we will explore a cutting-edge topic that sits as the intersection of analytical chemistry, digital technology, and food safety, that is artificial intelligence in food safety, enhancing detection of adulterants and contaminants. And to help us today to explore this interesting topic, we are very happy to welcome Professor Miguel Palma, as well-known expert from the Department of Analytical Chemistry, University of Cadiz, Spain. I will read the curriculum vitae. Professor Miguel Palma earned both his Bachelor in Chemistry and PhD in Science from the University of Cadiz. He currently serves as a full professor and has made a major contribution in the fields of fast analytical method, spectroscopic analysis, and innovative extraction technology. With over 240 articles, including 185 articles in Quartile 1 journal. So Professor Miguel Palma works has had significant scientific impact, particularly in the application of spectroscopy and machine learning for the food authentication and safety. And Professor Miguel Palma has also had strong international collaboration, including as a visiting professor under Indonesia World Class Professor Program at Universitas Gadjah Mada for multiple years, and as a lecturer in Erasmus Mundus and Southeast Asian and European Union programs. So, Professor Miguel Palma, in this session, you have 60 minutes for the presentation and 30 minutes for discussion. So without further ado, let us warmly welcome Professor Miguel Palma to begin his lecture. Professor Miguel, the time and screen is yours.
Okay, thank you very much for the presentation, Intan. I also thanks the organizing committee for inviting me to this summer course. It is my pleasure participating again in a summer course by Gadjah Mada. Then it is very interesting for me because I realize that you have excellent students attending this summer course. I'm going to try to introduce you to the topic. So let me try to share my screen. I think you can see my second screen now. So the topic is related with the application of artificial intelligence in food safety in order to detect both adulterants and contaminants. I am going to review 4 main topics. First, I'm going to run an overview about the problem, about the situation. Later, I'm going to present you the analytical tools that are going to help you to detect both contaminants and adulterants. Later, I am going to describe the main data analysis techniques, allowing you to apply machine learning techniques in food analysis. And through this presentation, I'm going to use some of applications we developed in our research lab. First, there is a global challenge related with the food analysis in order to determine either contaminated or adulterated foods, mainly because many of us, we are going to be related with these problems when we are consuming food, because in many cases we are going to consume either adulterated or in some cases contaminated food. It is really a economic problem because the expenses related with medical issues related with contaminated food or even adulterated food is quite high. And there are thousands of people that are going to be injured when consuming this kind of not good food, the food adulterated or contaminated. Food adulterants and food contaminants can be the same compounds, can be different. The main difference is from an analytical point of view between adulterants and contaminants, it is just the purpose. I mean, contaminants are not intentional compounds in food. However, adulterants, it is an intentional addition of this kind of compounds because some people is producing some adulterated food. From the analytical point of view, maybe contaminants are going to be in lower levels. So in some cases, we need quite sensitive analytical techniques. However, when dealing with adulterants, maybe the problem is going to be even worse because when someone is trying to produce some adulterated food, usually that people are going to try to do the best to avoid the adulterants. I mean, they are trying to mimic the new compounds in the food with the regular compounds in the food, trying to prevent the detection of the adulteration. So in both cases, we have to deal with some specific hard problems when trying to determine any additional compound in a regular food, either contaminant or adulterants. So in both cases, we have to develop quite sensitive and quite reliable analytical techniques. The problems are related with the final result of adulterated or contaminated food. In some cases, there is a problem with health risk because contaminated food can produce quite big injuries. In some cases, there are economic impact because when a food is adulterated, obviously, there is someone who is trying to get some economic benefit. In both cases, the final result is the loss of the consumer trust. I mean, we have to realize that when contaminated or adulterated food is arriving to the market, the final result, the final problem is that the consumers are not going to trust in the regular providers, so producing additional economic impact. When we are dealing with an analytical issue related with the determination of contaminants of adulterants, usually the traditional methods are going to be time-consuming, in many cases quite intensive labor, and in many cases also we have to get some false positive result because the sensitivity is in many cases not the right one to determine very small amount of compounds or very related compounds with the regular compounds in their food. So we need new detection methods. And new detection methods are not only detection method talking about the analytical techniques. But when talking about new detection methods means that we need a new tool in order to both to analyze the sample and to analyze the result, the data from the sample. I mean, we are not going to deal with only some analytical methods, but we are going to deal to an analytical tool taking us from the sample to the final result. I mean, we have to apply new analytical methods in order to generate a really huge amount of data, and that data must be converted, must be transformed in a final result, informing us about the presence or not of contaminants and adulterants. I mean, we don't need to think only about the specific, for example, UV visible method to determine one compound, but we have to deal with the whole analytical tool in order to reach the final result. I mean, there is or not, or there isn't adulterated or contaminated food. That is going to be the final result. So we are going to use artificial intelligence, mainly machine learning techniques, in order to help us to go from the input data, I mean, the data we are going to receive in our labs, to the final action. The final action is there is a contaminant or there isn't a contaminant inside the food. So in this case, we are going to put together analytical result with machine learning techniques, with artificial intelligence, in order to produce a tool allowing us to determine the adulteration or the contamination of food. This is the idea. I mean, we are not going to be stopped at the end of the result in the lab, but we are going to be in the right way to conclude the final conclusion. There is or there isn't contamination in our food. We are going to use mainly a spectroscopic method. A spectroscopic method supported by artificial intelligence. And why this combination? Because first, we are going to have very short sample preparation. I mean, we usually had to do nothing with the sample, just measuring the spectroscopy properties. We are going to run very analysis. If you are familiar with any kind of analytical procedure in a regular lab, usually it takes at least 1 hour between sample preparation and the final result. In our case, using spectroscopic method, spectroscopy-based method, we are going to run the analysis in a few minutes. And it is our duty to be able to produce accurate results. And the accuracy of the final result is going to be supported by artificial intelligence. This is the idea. Fast method, no sample preparation, and high accuracy regarding the determination of adulterants and contaminants. We should be able, for example, to determine some kind of microbial contamination using imaging analysis by microscopy or by regular cameras. We should be able also to determine some chemical contamination using some spectrometry data, trying to find, for example, pesticides, residues in any kind of food. And we should be able, for example, also to determine any kind of physical particles, metal, glasses, or plastic inside food using imaging analysis. And the idea is that we are going to get some data using some spectroscopic techniques that must be transformed in the final result. There is or there isn't this kind of contamination. The common techniques using in this kind of analysis are going to be hyperspectral imaging, near infrared, medium infrared, ion mobility spectroscopy, mass spectrometry, and in some cases, Raman spectroscopy. I guess some of you have been related in the past with this kind of analytical techniques, most likely some kind of basic spectroscopy in order to determine some specific compounds. We are going to move to the next step, is using the full spectra instead of specific signals. This is the idea. We are going to prepare some algorithms in order to analyze the spectroscopic data. We can talk about double analysis. The first analysis is going to be the analysis to be done inside the lab. The second analysis is the analysis of the data produced in the first analysis. So we are going to have two different steps. And later, we are going to create some models, and that models are going to be applied to even apply quality control in the processing line during the food production. So we should be able to develop double analytical methods in order to get the result directly in the processing step of the food. So we are going to have always three different steps. The first step is the learning process for the algorithm. The second step is the production of the model. And the last step is the application into the sample. This is a different process than the regular analytical procedures. In the regular analytical procedure, we don't need learning process. We don't need algorithms. We just need a calibration curve. Later, applying the calibration curves. In this case, we have to teach our algorithms in order to train the algorithms to prepare the models, and finally to apply the prediction of the determination in the real food. So this situation make us to be familiar with some kind of algorithms and with some kind of new data from the analytical process. The benefits. We can get near or even real-time application, I mean on-time result from the analysis. We are going to reduce the number of positive or false negatives. We are going to reduce the manual work. Then, if they are not human work, or we are reducing the human work in the analytical procedure, we are going to reduce the human errors for sure. We can even develop some warning system. I mean, we can even try to predict how to evolve during the production. We are going to reduce risk and also wastage, because it is supposed we are not going to use reagents during this kind of analytical procedures. And for sure, we are going to increase the reputation of our companies, because we should be able to run very good quality control during food production. So let me show you now some basic information about the analytical tools you can use to produce this kind of final methods. And I need to review some basic points, because if you have been related in the past with analytical procedures, we have to think in a different way in order to get this new method. And the first point is calibration. I mean, calibration is the way for you, for any of us, to try to develop some relationship between physical properties we are going to measure in the lab with the concentration of one specific compound into the sample. In this case, the concentration should be the concentration of contaminants of the adulterants. In order to do that, the first step is the preparation of standards. I mean, we must have the standard of the adulterants, then prepare usually some solution, then analyzing the solution, and finally preparing a calibration curves. And these are two typical calibration curves. I guess many of you, maybe most of you, have developed some calibration curves in the past. When we prepare calibration curves, we usually run a regression result in order to get what is the relationship between the signal and the concentration, and then we are going to apply it for the determination into real samples. However, before application of this calibration curve, we have to evaluate if the regression is the right one or we can improve the regression. In this case, I am showing you two different calibration curves. The first one is a calibration curve with a regression coefficient 0.995. The second one has a regression coefficient of 0.9998. Most of us, we can say that calibration 2 is better than calibration 1 just because the coefficient of regression is much better. It's 3 9s and 1 8, 0.9998 here versus 0.995. So it looks like calibration 2 is better than calibration 1. However, let me take you to a different point. This is, again, the two calibration curves. And now, using calibration 1 and calibration 2, I am going to try to determine if I am able to measure 4.5 ppms. I mean, as you can see, the x-axis is from 0 to 10 ppm. Then I'm going to try to measure 4.5 ppms using calibration 1. As you can see, using calibration 1, if I have 4.5 ppm in my sample, I should have a result, an intensity result, around 55 millivolts. So if I have a spectrometer that it is able to measure only numbers without decimals, it means that if I have a system that it is not able to provide me 60.1, but only 60 or 61, using calibration 1, I am going to be able to measure 4.5 ppm because the answer should be more or less 55 millivolts. If I do the same using calibration 2, it means 4.5 ppm, the intensity should be 14.5. However, I mentioned before that our system is not able to provide decimals, just measuring 40 or 50. I mean, 14 or 15, sorry. So if the system is able to measure only 14 or 15, using calibration 2, I cannot measure 4.5 ppm, just because the resolution of my spectroscopy system is not able to provide decimals. What is the key point? The key point is the slope in the calibration curve. As you can realize, calibration curve, the slope is 10.8. The slope for calibration curve is only 1.0. So the larger, the higher slope in our calibration curve, the better for us, because we are increasing the sensitivity of the method. This is quite important. We have to provide high sensitivity in our calibration in order to be able to determine small differences between the samples. So we have to pay attention to the coefficient of regression, for sure. We have to produce very high regression coefficient. However, it is even more important for us to get very high slopes in our calibration curve. As you can realize here, using the same system, I can determine 4.5 ppm or not. Even I can even determine here 4.1 or 4. Here, I can go directly from 4 to 5. So this calibration curve is much better than this one because the slope is larger. I'm going to be back to this step in a few minutes, but remember that I think I demonstrate that the slope is quite important for calibration. Okay, let me discuss about a different point now. When calibrating for concentration, we are going to produce a final result that it is informing us about the level of one specific contaminant or one specific adulterant. However, we have to think about what is our interest. Do we need to determine the level of one specific contaminant, or do we need to know if our sample is contaminated or not? I mean, of course, both answers are going to be related. If the level of the adulterant is larger, or the contaminant is larger than 0.1, then the sample is contaminated. If it is lower than 0.1, maybe the sample is not contaminated. Just in case 0.1 is the border about having or not having contamination or adulteration. However, when we are producing food, we should be centered about what is the situation of our food. Are we producing contaminated or adulterated food or not? So it's just a very simple answer, yes or not. It is much more simple, much more important, much more useful than the knowledge about 0.1, 0.1, 2, 3, or any different data. Let me try to take you to this situation. If we are able to develop a calibration cure in order to determine the age of people, maybe we should have a calibration cure. In this case, it's not a line, but more or less it's like a cure. And later, following with this calibration, when we have some people who don't host, we don't know what the specific age, maybe we can apply the calibration cure in order to get the age of the people. Let me show you an example. Joe Biden, the former president of the States, and Robert De Niro, both of them, they are 81 years old. If we have a calibration cure informing us that both these two people, they have 81 years old, maybe we have the right information because they are old. However, do you think that the general health situation for Joe Biden and for Robert De Niro is the same? Maybe, I guess you are related with the final situation of Joe Biden during the votation in the States. The health condition not so good. However, Robert De Niro with the same age, this is a very much better health condition. So what is the interest for us? Is the number, 81 years old, of the general health condition for this kind of people. So we have to think that in some cases, even much more important than we to know what is the specific level of one compound, is the general situation of the food sample. We should be ready to calibrate indexes instead of a specific concentration. When calibrating indexes, we have some problem because we don't have standards for indexes. Index is the general health situation for the people, for example. However, it is quite much more important than the specific age for these people. Let me talk now about a different situation, the situation about food sample. If you have been working with any kind of food in the past inside the lab, for sure you realize that we are dealing with complex samples because the matrix for food contains thousands of different compounds, thousands of different levels for that compounds. In some cases, even the sample is not stable because it can evolve very fast due to heat, light, or air. So we have to run very fast analysis and we have to receive very fast answer in order to be able to modify the production processes. So working with food sample, it is quite important to realize about the complexity of the matrices that are going to produce that we are going to have a specific problem during the analysis. We should need fast or sensitive analytical methods in order to work with food sample. Now, a different topic is about separation or spectroscopic methods. I guess most of you have been related in the past with some kind of analysis based on UV visible spectroscopy. Here I am showing you 3 different spectra using different concentration of one specific compound. The absorbance is increased when the concentration is moving from 0.6 to 1.9. And this is the regular answer. If you have been working with UV visible spectroscopy, that I am talking about this spectroscopy because it's quite basic. Usually, you have been working with only one wavelength. Most likely, you go to the lab, then running some determination and one specific wavelength, maybe 240, maybe 260. It depends on the specific application. However, I don't know if you realize it that you are working with spectra. I mean, usually spectrometer are recording the full spectrum, then showing you only one specific wavelength. However, you are collecting a lot of information. Information, in this case, for example, between 200 nanometers up to 300 nanometers. This is ultraviolet. The question is, I don't know if you realize that you are collecting many different data, then using only one data. Why one specific data? Because usually you are related with the determination of one specific. This is the typical spectrum, a continuous line through the whole spectrum. In this case, ultraviolet, but it is possible also visible or infrared. When we are dealing with chromatographic methods, always, we are going to get chromatograms. Chromatograms is kind of figure. It means that compound 1 and 2 are eluting together from the column. Compound number 3 is eluted at 10, maybe 30 minutes. Then 4, 5, 6, until the last compound. They are going to be separated in the chromatography system. This is liquid chromatography. This is gas chromatography, providing you the specific level, the specific concentration for different kind of compounds. In this example, with some names. For example, linolol, cineol. I mean, we can even identify compounds. Then the final result from chromatographic analysis usually is a table containing names or number for the peaks, plus the area or the ppm or the milligrams per gram or the final concentration of that compound. I mean, the regular result from these two analytical products, it is a table containing maybe 10, 12, 25, 30 different compounds. Let me take you now to this figure. This is the result of a mass spectrometer analysis. Maybe after a gas chromatography system, maybe after a liquid chromatography, or maybe a direct analysis. It doesn't matter. But as you can see here, it is quite similar to a chromatogram. However, here we don't have a table, but we have a spectrum. This is a spectrum. What is a spectrum? A spectrum is the specific signal received by the detector, in this case, at different NZ ratio. However, visually, it's quite similar to a chromatogram. So the question is, why this result is as a spectrum and one is received as a chromatogram? The main reason is that here, each signal is due to a different compound. However, here, all the signals are reporting the level of the same compound. We are producing fragments, but we are recording only one compound. Here, we are recording many different compounds. So this situation should be quite important for us, because we are going to work basically with spectroscopic information. However, we have to realize that using spectroscopic information, we can have also information about individual compounds, because we are able to record the information individual compounds, however, together without separation. So the situation is that using a spectroscopy, we can get information, very detailed information about individual compounds or about joint compounds into a sample. So the idea is, what is best, chromatographic or spectroscopic information. For sure, chromatographic, because there is information about individual compounds. However, chromatography takes time. In this case, for example, 25, 30 minutes. In this case, almost 6 minutes. So even with lower quality information that it is a spectroscopy, obtained in maybe less than 1 minute, we can use in the same way than chromatographic. I mean, we can use individual determination for the signal at different wavelengths. In the same way, here, in the chromatographic information, we can get individual detailed info at different times. So we are moving from time to wavelength, but also very detailed information at different wavelengths. So this is the idea. I mean, if you in the past have been related with chromatographic analysis, you have to realize that you are receiving detailed information at different times. Now, moving to a spectroscopic analysis, we have to think that we are going to receive detailed information at different wavelengths, but also quite detailed information. So both kinds of methods are quite interesting for food analysis. However, spectroscopic methods need less analysis time, faster. They are going to produce faster results, and they are not going to use reagents, so not producing wastes. Okay, now let me back to calibration again. And why to be back to calibration now after we review the situation with spectroscopy and chromatography? Because I'm going to propose you to modify the regular way to use spectroscopic information. As I showed you before, when running a calibration cure using, in this case, spectroscopy, we are going to have the full spectrum. This is from 300 to 600. This is a visible spectrum. And we are going to follow the regular procedure, then running the analysis on only one specific wavelength. In this case, I choose 454 nanometers. Then I'm going to collect the information by different standard solution from 1 to 9 ppms, then collecting the absorption, the signal, and 454, this specific information, then using the data to prepare a calibration curve. In this case, I prepared this calibration curve with good coefficient of regression, and the slope is 0.0, almost 0.08. So I wonder if I can choose a different wavelength. For example, instead of using 454, I can use also, not instead of, but also 453 and 455. I mean, is there any problem if I use together the information from 454, 453 and 455? In principle, no. I was choosing 454 because it is the maximum. So the maximum means the highest sensitivity I'm going to get in the method I am developing. However, if I am able to use also 453, for sure, the calibration curve is going to show us a lower slope. I mean, because the absorption in this column is lower than here, the final slope in the calibration curve is going to be lower. However, what about if I put together the three values? What about if I use this value to prepare the calibration curve? Not this value individually, nor this value individually, nor this column individually, but all of them together. 15 plus 14 plus 14 is 0.43. If I do that, I'm going to have this calibration curve with the same regression coefficient. However, instead of 0.8, I'm going to get a slope of 0.24. It means much larger sensitivity. You have to realize that at this stage, I am using the spectroscopic information as I usually do with the chromatographic analysis. I mean, I am going to use the whole information, not only one specific wavelength, but the whole information. Then, in this case, I'm going to increase the sensitivity of the method. That it was the first point I was discussing. I mean, it is quite important for us to increase the slope, because increasing the slope, I'm going to be able to determine minor differences between the sample. And remember, contaminants are going to be at very low levels. Adulterants are going to be tried to not to be determined easily, because they are trying to pick the sample. So we have to improve the analytical method. We have to increase the scope of the calibration curve in order to get better result in the determination of adulterants and contaminants. And the next question is, why only 3 wavelengths? Why not the whole area? Why not from 300 to 600? This is the key point. I mean, using spectroscopic information, you are going to get a lot of different information from different compounds. So the idea is using all the information you are going to get in your spectrophotometer. In this case, most likely, in the case going from 1 to 3 wavelengths, we are increasing the slope by 3, sorry, 0.8, 0.24. If we are using 300 different wavelengths, most likely we are going to multiply the slope by 200, 250, even 300. So the idea is we are going to get much better calibration using multivariate calibration. This is the key point. Using this kind of approach, we need a lot of information. Then we have to apply multivariate calibration. Univariate calibration is not going to be available any longer. So let me show you now an example we developed in our lab related with the adulteration of honeys. Honeys can be adulterated very easily. Okay, the first adulteration step is adding water. I mean, the idea is to get a cheaper product, because we can use the regular honey, then adding small amount of water, then put in the market adulterated honey with water. However, if we adulterate with water, the situation is that the level of sugar is going to be lower than regular honeys. Then people, in order to guarantee that adulteration with water is not detected, they are adding high fructose corn syrup in order to adulterate honeys. The point is that high fructose corn syrup is mainly glucose. And the main compounds in honeys also are glucose, I mean sugar, carbohydrates. So there are small differences between the adulterant and the regular food. In this case, the problem is quite difficult, because if we determine the level of carbohydrates, we are going to get the same result for pure honeys and for adulterated honeys, because it can be fixed during the adulteration. So, additional points. If we go to a different analytical techniques, in this case IR, medium IR, we can establish what is the specific spectroscopic regions for the compounds in honeys to produce signal. And let me do a fast reviews about the composition of honeys. It is mainly glucose, fructose, and other sugars, then water, some vitamins, and some phenolic compounds. Okay, here you can realize about glucose is producing signal at different weight numbers or different frequencies or different spectroscopic regions. Water is also producing a lot of different signal. Vitamins are producing signal at different wavelength. Why? Because the signal in the medium IR spectroscopic regions are related with the chemical bonds. I mean, any compound containing a chemical bond between carbon and hydrogen is going to produce a signal around 3,000 frequencies, centimeters minus 1. Every compound containing a chemical bond between oxygen and hydrogen is going to produce an absorption about 3,200 more or less. So we are going to have a quite complex spectra from this kind of sample. We will use only one frequency in order to determine glucose, because when glucose is producing signal, fructose is also producing signal, also cellulose, in some cases some phenolics, in some cases some vitamins. So the problem is quite complex. So several different compounds are going to contribute to the same signal. What can we do? Let me try to explain the basic for the multivariate calibration. Okay, in order to explain the situation and the way to solve this problem, I'm going to use a bit more simple spectra than IR spectra. This is the IR spectra for aniline, and this is the IR spectra, the UV spectra for vanillin. Same compound, different spectroscopic regions. I'm going to use UV because I think it's going to be a bit more clear for you to realize about the situation. Okay, if I have this compound, compound A, and I have another compound, compound B, with two different spectra, two different compounds, two different spectra. If I put both of them together in a solution and I record the spectrum, I'm going to get a combined spectrum from both of them. Combined means that I'm going to put together the absorption by compound A plus compound B. So this is compound A and this is compound B. So this height in the joint spectrum is going to be a combination for the signal from compound A, the concentration of compound A, plus the concentration of compound B. In both cases, multiply by the specific properties of compound A and B. So if I measure this height, I'm going to get this contribution. If I measure the height at 295 nanometers, I'm going to get this. It means the signal of the joint spectrum is a combination applying the Lambert-B law from both compounds. So if I have this information, I can get some additional information if I am able to realize what is the relationship between the signal from compound A at two different wavelengths and the signal from compound B at the two different wavelengths. I mean, using these two equations, I don't know what is the concentration of A. I can get from the spectra of the pure compounds the absorptivity coefficient for this specific wavelength for compound A and B, for compound A and B at 295. However, I don't know what is the concentration of compound A of B. Then, if I have these two equations, however, I have 6 different incognita, I mean 6 different non-known values, then I need additional equation. Then I'm going to look for these two equations. Can I know what is the ratio between the absorption for compound A 295 and 271? Yes, I can do it because I can record the specific spectrum for compound A, and this is the ratio for A and the ratio for B. Then I am able to get 2 additional equations that I can get the information from the specific spectra from the pure compounds. So if I know the identity of the compounds and I know the spectra of the compounds, I can get a system with 4 equations, however, still 6 non-known values: CA, CB, AB, and 295 and 271. So how can I solve this situation? Very easy. Can I get additional information from the spectra? Yes, because I am using only 2 wavelengths. However, in this region, I have from 240 maybe to 380, I have 140 different wavelengths. Then I can prepare equation like this one for a number as high as 140 different equations. So can I solve this problem? Yes, I can solve this problem because I can record the absorption of the joint sample, then applying equation to determine the concentration of A and the concentration of B. So it can be solved. However, what is the starting point? The starting point is that we need more equation than components. However, the key point is that we have a lot of information from the spectroscopic analysis, hundreds of different wavelengths. So it is possible to get hundreds of different equations. But the starting point is that we cannot solve all the problem because we don't know how many different compounds are going to be found in a food sample. I mean, this solution is working for a mixture of 2, 3, 4 already known compounds. However, we have no idea about how many different compounds we are going to find in a sample. We have no idea about what are the spectroscopies of the compounds in our food sample. So even if we are able to prepare 1,000 different equations, we cannot get the information from the specific compound. So this solution is allowed for us to determine the contribution of 2 different compounds in a mixture. However, it is not working for food sample. What is the solution? The solution is, instead of using standards, we are going to use samples to prepare the calibration. I mean, instead of using a specific standard, we are going to use samples with already known concentration of the adulterant of the contaminant. Then we are going to get, for example, 10 samples. However, the key point is that our sample already determined by a previous reference method contains some errors. Because when we determine that the level of the contaminant is 1.23, our reference method is going to report us that the level is 1.23 plus less 0.06. It means that we are going to receive data for calibration with errors. So can we do regular calibration curves? No. We have to apply multivariate calibration curves. Why? Because first, we have not information about how many different compounds in the sample. And second, we have some data from the reference method with already errors. I mean, we don't have exact standards, but we have sample with some errors. So the idea is we are going to try to do calibration using sample instead of a standard. And there are some consequences. The consequence is that because we cannot have, we are going to have errors due to the matrix. We don't have information about other compounds in the matrix. So we don't know how many compounds are contributing to the signal. So the problem is a bit more difficult than univariate calibration. Some consequences, yes. We cannot calibrate with regular standard. We need many different samples to be determined by a reference method before starting calibration, and we have errors bigger than the regular reference method. This is the consequence of using multivariate calibration. Remember, using the whole spectrum in order to prepare calibration.
I'm sorry, Prof. Miguel, for interrupting you,
yes?
but you only have 15 minutes left.
Thank you very much. Then I'm going to leave the couple of videos I was trying to use for the explanation for you to review directly. You have the reference over there. Okay, so there is one important point you have to realize. When you are running calibration, you are running your own calibration in your own lab in order to apply on your own sample. I don't know if you realize that using a common calibration between different labs, it is possible. I don't know if you have been related in the past with this kind of calibration. However, if you are using a spectroscopic system and you are going to run calibration using real samples, it is possible for other labs to send you the calibration. Why? Because it is possible for a spectroscopic system to use some specific reference material, providing you what is the spectra your system must provide for this reference material. So it is possible, if you apply this correction, to share the calibration with any other lab around the world. So it is quite much interesting than running your own calibration. Usually, the regular number of samples we need to run this kind of calibration is between 100 to 1,000. In most cases, we don't need to run this calibration, but other people already did using a system in a different lab, then sending the calibration together with the reference material, allowing you to, the name is to clone your system with a system in a different lab. So quite interesting. Okay, let me go back to the second point of the presentation, and I'm going to try to be on time. What to do about the data we are going to receive from the analysis? The data are going to be really a very large amount of data. What to do? Okay, we are interested in the level of the adulterants or in the level of the contaminants. However, the real question is, can this food be consumed? Can this food be sent to the market or not? This is the idea. So instead of numbers from one specific compound, we have to say just pass or not during the production of the food. Pass means sent to the market or not. So it is better to have just an image of the sample. A final index is similar when we are trying to identify people using fingerprints. Is this people or not? Is it as simple as yes or not? So the idea is that after using a spectroscopic analysis, we have to apply data analysis in order to make the result from the spectroscopic analysis reliable, fast, and the right one for us to be able to provide the final answer. So the idea is, if we have a chromatographic analysis, do we need the information about individual compounds in order to get the final answer about the sample can be sent or to the market? The answer is no. We don't need a very detailed information, only a fingerprint. So machine learning is going to move the data you collected in the previous analysis in the multivariate calibration to useful information. Let me pass a bit faster in this area, but the key point is we need a very large number of known samples in order to train our system, later to validate our system, and finally to apply. What means training? Training means that we have to pass already known sample, in our case is honeys, through our system in order to our system to realize what is a high quality honey. Then, using the analysis of the spectroscopic, we are going to apply different kind of machine learning techniques in order for the model to use a lot of information to prepare models to identify high quality honeys. And this is a key point. We can update our method through time. I mean, this is not a final method. The method can be improved at any time because we can redo and redo the data analysis. We can improve the calibration every day. So we can make a better training to our system. And now let me try to describe some basic methods about machine learning. The first one is pattern recognition. This is I guess you understand that the idea here is try to recognize people using some specific points in our face, or trying to recognize how any of us are writing, trying to make models of specific letters. So this is the idea. So the classification techniques, for example, for this kind of apples, can be applied trying to make lower the variability inside a group and make very large the variability between different groups. For example, if we measure the sizes of the apples, most likely we are going to have a good variable in order to discriminate between the big ones and the small ones. If you use the color, we are able to discriminate between red and green apples. However, if we measure, for example, the level of sugars, maybe that variable is not going to be useful to discriminate between red and green just because they contain similar level of sugar. So the key point is, in order to classify, we have to compare and to maximize the variability among different groups. So we have different kinds of techniques, machine learning techniques, supervised and non supervised. The main supervised, non-supervised techniques are the clustering and the techniques devoted to the reduction of dimensionality. Supervised techniques are ready to run prediction. I mean, in this case, they are the final techniques for us to determine adulterants or contaminants in the sample. They are classification or regression techniques. Let me try to review some of them. Okay. And let me try to now trying to explain you what is the main difference between supervised and non-supervised. The non-supervised techniques, we don't know what are the groups. Obviously, here there are some groups that the group is yellow, red, or green apples. However, when running the data analysis, we don't provide that information to the algorithms. We are providing just the spectroscopy result. So the final conclusion is that maybe the system is going to be able to classify the samples by sizes, for example, sorry, by color, not by sizes. So this is a regular grouping result from this sample. What about supervised? Supervised is that we are going to provide information about this sample are green, this sample are yellow, this sample are red. So when we have a non-noun sample, the analysis is going to classify this sample between green, yellow, and red. Non-supervised techniques are not able to allow us to classify new samples. Supervised techniques are going to be able to classify samples because we are informing about group A is the group for green sample. Group B is the group for yellow apples. This is the main difference between non-supervised and supervised techniques. What are the best techniques? Both of them. Non-supervised are the starting point for machine learning techniques. Supervised are the final techniques in order to get numerical results. So let me show you our result with, in this case, with vinegars, trying to determine the production way for vinegars, trying to avoid adulteration. In this case, vinegar was produced using very fast way or the regular way, the traditional way. However, in both cases, vinegar is a mixture mainly between acetic acid 6 to 7% in water and other compounds. So there are two ways to prepare vinegars, and there are people trying to use the very fast fermentation in order to avoid the very slow, typical traditional fermentation to produce vinegars. So what we do, we are collecting samples, not applying any kind of treatment, just filtering the sample, then measuring the FTIR properties. And this is the result from 86 different samples. Visually, we can find some differences between the sample. However, I guess all of us agree that using visual analysis, we are not able to determine what sample was produced using the regular traditional fermentation versus the very fast fermentation. I didn't mention the regular time for us to collect a FTR spectrum is 1 minute. So what is the purpose of hierarchical cluster analysis? It is a grouping technique, non-supervised grouping technique. Produce groups without specific identities, just for us to realize about what is the structure of the sample. And this is the result we get from our sample. We have a lot of sample from one specific grape variety fermented in oak barrel. We have the acidification process conduced into a different group. However, there is a mixture between different clusters and other varieties. So cluster analysis is informing us that using FTIR, it is possible for us to make groups. Cluster analysis is not producing groups. but it is informing about the structure. And this is the result. We have new ways to see the same result. I mean, in this case, different colors and different dendrites are informing us about different production ways for vinegars. But the idea is, looking at this figure, it is for us to propose this data to be used to classify using as supervised techniques. There is a new kind of dendrogram, in this case circular, that it is very useful for other kind of sample. The second technique is PCA, Principal Component Analysis. In this case, we are trying to modify variables. If you remember when I mentioned using UV visible spectroscopy ranges, we are moving from 200 nanometers up to 700 nanometers. It means 500 different numbers. Using 500 different variables, it is not possible for us to process samples containing 500 different data. However, the key point for principal component analysis is moving from new 500 variables, combining the 500 starting variables to new 500 variables, however, putting together all variability in a reduced number of variables. And the idea is for us to create this kind of new distribution. I mean, in this case, I think it is clear that we can discriminate, we can separate green samples from blue samples if we know what is the value for PC1. PC1 means principal component 1. Principal component 1 is a new variable that has been prepared using a combination of the 500 starting variables. In the same way, PC2 and the remaining PC3, PC4. So PCA is allowing us to put together important variables, allowing us to make groups in our sample.
Prof. Miguel,
Let
you
me try
only
to
have
explain.
5 minutes
Thank you very
extra
much.
to finish your
Okay.
topic.
I appreciate. There is only, I think, 10 additional slides. Thank you very much. I'm sorry for this extra time. Let me try to present the result using the apples. The idea is that if we have information from the apples, we are looking for PC1 that it is separating apples by sizes, then PC2 that it is the variable allowing us to separate apples by color. This is the idea of PC1, PC. How many PC do we need? It depends on our samples. This is the contribution, the explanation for the preparation of PC1 and PC2, and this is the final result from our study on vinegars. We need 3 different PC in order to separate the different vinegars. Okay. And finally, what are the discrimination techniques or the classification techniques? Remember that now we are moving to supervised techniques. In this case, we are preparing a model in order to classify this sample. The sample, in this case, is going to be classified due to the color. However, the idea is to create groups between adulterated and not adulterated sample, contaminated or not contaminated sample. Then the new sample is going to be located in one specific group. In this case, we have to train the system. And training means we must pass through our system a lot of different samples without and with contamination, without and with adulteration. And finally, we have to apply to the testing set. Okay, there are different quite models for you to evaluate the method. I'm sorry, I have no time, and I would like to finish with the examples of machine learning applied to adulteration. So here you have 3 links to our result. And this is the final demonstration about first, results can be shared with any other lab around the world. And you can measure, for example, let me go to a different, sorry, let me try, sorry. Yes. Only 1 second, please. Hold on, please. Yes. The links I am providing you are these specific places. This is an app prepared using machine learning with spectroscopic data. Maybe I can go directly to the last one. It is related with the identification of adulteration in fruit juice. The final result should be as simple as this one. You can upload, let me upload one specific data set. This is the data from a spectroscopic method from 1.02 to 1.29 absorption in ion mobility spectroscopy. There are 3 samples. If these 3 samples can be produced in any of your lab, if you are interested in the determination of the adulteration of any fruit juice, then you can upload to this web page. In this web page, we have already uploaded our method to determine the adulteration level. If your ion mobility spectroscopy system is cloned with our ion mobility spectroscopic system that it is possible, you can upload the result, then analyze your sample using our calibration model, using our machine learning techniques. And the result is that the first one is adulterated using 48.5% of adulteration with one specific grape juice. The second one is 1.6, and the third one, the pineapple, is pure. We are uploading our calibration curve, and you can see where your samples are allocated between our samples. So you can realize about the similarity of your sample with the sample we use for the calibration. You even share the principal component analysis result, and the black points are your sample inside our model. And then, using machine learning techniques, it was possible for you to realize if your sample has been adulterated or not online with a calibration that we developed here in Cadiz. And maybe you can run the analysis in Yogyakarta. Okay, and just to finish, only 1 minute. Some final remarks for any of us to realize about, yes. So, what is the pending issues? First, collecting sample. Second, developing calibration. And finally, trying to the regulatory standards to accept the method developed using artificial intelligence, machine learning on spectroscopic data. We are in the way, but still some pending work. So the final remark is that food safety is going to be supported by artificial intelligence in the next years, because it's the only way for us to reach very high, very fast and reliable analytical methods. So I was using more time than expected. I'm sorry for this extra time.
It's okay, Prof. Miguel. I'm so sorry. Unfortunately, your time is up, but thank you very much, Prof. Miguel, for that true and a opening presentation. I know it's kind of hard to explain all this interesting topic in just 1 hour. So now let's move on to the Q&A session. We'll begin with 2 questions. If we still have time, we will be happy to accommodate additional one. So for all participants, you are welcome to raise your hand or type your question in the chat box, and I will help to lead the discussion. So the first question, okay, Michael.
Check.
Uh, Thank you for having me. My name is Miguel and I'm from Gadjah Mada University, Indonesia. So I have a question. Uh, this topic is really broad, right? And I'm a little bit overwhelmed when I'm listening to this whole topic. So, do you have any recommendation of, let's say, fundamental to understand more about this topic? Thank you. That's my question.
Um, you are invited to come to Cadiz if you want to learn directly on the techniques. There are several videos through YouTube if you want to learn about spectroscopy and machine learning. It is a topic that it is in the way right now. We have some papers already published with this kind of methods. In every paper we are publishing, we are including the app for you to upload your sample if you want. And even we are developing a new web page for us to guide people to this kind of techniques. It is on progress. There is a very initial version of the web page, and we are putting together all the apps. We are starting with this kind of apps 3 years ago. I didn't show you, but the first two apps are very basic, just a table producing the information. However, right now we are including a lot of tools in the same app. I mean, you are able to see what happens if your sample is going to be a bit larger or a bit shorter in some specific wavelength. So I can provide you later, I can include in the final presentation the web page of our research group for you to be able to review this new version of the tools.
All right, and lastly, if it would be possible for you to upload the PowerPoint so that we can study it again later.
It is my fault. I didn't send to the organizing committee. They request the version. The PowerPoint presentation is a bit big. I think it's 32 or 34 gigas. Then for sure, the PDF version is going to be sent. And I'm going to do the best to send also the PowerPoint presentation, sure.
All right, thank you for the answer.
Okay, thank you, Professor Miguel, for answering the question. There is second question on the chat box. It's from Norquin. The question is on the chat box, Prof. Miguel. Is there potential for AI enhanced portable device to conduct contaminant detection in field condition in food industry?
I mean, first, it is in my opinion, maybe it is a double question. The portable means that we can take the system outside the lab. The answer is yes, of course. But maybe it is even more important. We are working with some companies in order to put, in this case, on near system with filters. I mean, not collecting all the information, but near system recording continuously the production of oils, for example, olive oils. So there is a continuous information about the composition of oil leaving from the oil tank. So it is possible to record, to run determination directly on the production line. So it's not only portable, that means that we can take to measure, for example, fruit in the fields. We have a portable NIR to measure the level of sugar in grapes directly in the fields without taking the grapes from the plant. But there is also the option for the food companies to put NIR system directly in the production line. So there is a continuous determination of the composition of the sample while processing the sample. Yes, of course, portable means usually lower resolution, but still enough to get very good data.
Okay, for Norquin, is that answered your question? I hope yes. Yeah. So everyone, I still open for one additional question. Anyone here or from the Zoom? No, really? Oh, yeah, Fatra.
Good afternoon, sir. I would like to ask if can spectroscopy
I'm sorry, maybe you can closer?
also detect microbial growth, for example, in meat or like disease, can also detect diseases, microbial growth, etc. Thank you.
Yes, sure. I mean, it is, in fact, it is very common to have spectroscopic techniques to determine what are the microorganisms infecting some injuries in medical application. So this is quite common, already established, about medical application to determine what is the reason for the infection. And in food, it is applied, for example, to determine what is the specific yeast producing fermentation in some fermented product, like wine, for example. So yes, the real situation is that spectroscopy is not determining directly the microorganisms, it's not identify the yeast, but it is collecting information about the secondary products from the yeast, mainly volatiles. This is very common using some kind of spectroscopy using volatiles. So it is possible to identify the yeast, determining the byproducts or the secondary metabolites from the yeast. So the answer is yes, but it is non-direct determination.
Is that answer your question, Patra? Okay, thank you so much. Because we only have a few minutes left, unfortunately, I need to end our insightful discussion. Thank you so much, Professor Miguel, for your thoughtful answer and more importantly for sharing your expertise with us today. And it has truly been an enlightening session. And thank you for everyone who joined us. We hope you found this lecture both valuable and inspiring. And now, let me conclude this session with a brief summary of today's presentation. So, Professor Miguel Palma explained how artificial intelligence, especially when combined with spectroscopy, can enhance food safety by rapidly and accurately detecting adulterants, contaminants, and microbial risks. This integration allows real-time identification of harmful substances, improving food quality control and consumer trust. And analytical techniques such as chromatographic and spectroscopic methods support this process. While chromatographic offers detailed compound separation, spectroscopy enables faster analysis but require multivariate calibration to ensure the accuracy with method selection depending on matrix complexity and detection goals. And the data analysis is strengthened through machine learning, utilizing supervised model, for example, classification, regression, and unsupervised model clustering, dimensionality reduction models, and yeah, pattern recognition help distinguish and classify sample by analyzing variability using tools like PCA, LDA, SVM, and RF random forest for model training, validation, and prediction. So for Professor Miguel, on today, like artificial intelligence in food safety enhancing detection of adulterants and contaminants, really highlighting and growing importance for integrating advanced analytical chemistry with intelligent technology to safeguard for quality. So thank you once again, Prof. Miguel, for the inspiring lecture and thoughtful discussion. Your insight into how artificial intelligence and spectroscopy can revolutionize food safety and authentication detection are not only timely but also crucial in facing today's global food challenge. So thank you so much, and to all participants, thank you for your active involvement. We hope today's session leave you with fresh idea and deeper understanding. So let's continue working together towards safer, smarter, and more sustainable food system. Wassalamualaikum warahmatullahi wabarakatuh. Om Santi Santi Om, and see you at tomorrow. Bye everyone. Thank you, Professor Miguel.
Terima kasih. Thank you very much for your attention. Bye-bye.
Thank you so much to Professor Miguel for being an insightful lecturer. We would like to give the appreciation certificate that will be given symbolized by our moderator.
Thank you very much. I'm very happy.
This is from us, Professor Miguel. I hope soon I can meet you personally to give this certificate for you.
Excellent. Thank you very much. It was my pleasure.
We will also
Bye-bye. Sorry? Okay.
Adios, Professor Miguel.
Yeah.
We will also give a certificate of appreciation to Miss Intan Dewi Larasati MSc. The certificate will be given by the chairman of 7 Summer Course Program, Dr. Fiameta Ayu Purwandari. Okay, and with that, the session for today have finished, and we also remind you to fill the attendance form for this fourth session that can be accessed on e-log and also given by committee in the group chat.
Also, we would like to remind all the participants for the post-test and group discussion assignment for today's activity. So the post-test deadline is 8 p.m. and the group discussion assignment deadline is 11:59 p.m. Thank you everyone for all the participation and attention for today. Have a good rest and see you again tomorrow. Assalamualaikum warahmatullahi wabarakatuh.